For decades, the primary bottleneck in software engineering was translation. A developer had to hold a human intent in their mind and render it into the precise syntax a machine could execute. Today, an estimated 41% of all new code is AI-generated. That bottleneck has collapsed. This timeline traces how the shift occurred, beginning in 2021 with basic autocomplete. The initial capability was limited to simple token prediction, guessing the next few characters inside a developer's editor. By 2023, chat-based interfaces allowed developers to describe entire features in plain English. Natural language became a functional programming interface, allowing developers to generate working implementations through conversation. That brings us to the current era. Fully autonomous agents can now clone a repository, plan multi-file architectural changes, execute them in sandboxed environments, and submit pull requests, all without a human typing a single line of code. With manual typing largely removed from the equation, engineering velocity is now gated by the precision of human intent. This rapid acceleration has split development practices into two camps. The first is vibe coding. A developer prompts an AI, copies any error messages back into the chat, and manually spot checks the output to see if it seems to work. Vibe coding has a low barrier to entry, but it carries immense operational debt. When outputs aren't systematically verified, teams fall into trial and error loops that burn tokens and degrade the context window until the agent loses track of the project's state. Teams building mission-critical systems rely on a different framework: agentic engineering. Agentic engineering focuses on wrapping an LLM in automated evaluations, CI/CD gates, and rigid execution constraints. The defining distinction across this spectrum is verification. Vibe coding relies on a developer manually running the code. Agentic engineering employs tests to verify deterministic functions and automated evaluations to score the agent's logic. Where a team operates on this spectrum dictates whether they are generating a disposable prototype or a resilient production system. This diagram outlines the core engine of autonomous development, the agent loop. While a chatbot waits, an agent runs continuously. It perceives a goal, plans steps, takes action, and observes results. If a test fails, it routes that error back, replans, and iterates. This loop requires specific information, context engineering. This chart compares static and dynamic context. Static context includes system instructions. It's always loaded, reliable, but expensive per interaction. Dynamic context handles specialized knowledge, retrieving agent skills or domain data only when a task requires it. Efficient enterprise agents are engineered with progressive context disclosure. This prevents token overload and maintains focus without flooding the model with irrelevant instructions. When an autonomous agent makes a mistake, developers instinctively blame the underlying LLM. They assume the model simply wasn't smart enough to complete the task. This equation isolates the reality of system architecture. The model is merely the raw reasoning engine. Everything else is the harness. This concentric diagram maps the 90-10 rule. The LLM is only 10% of an agent's capability. The surrounding machinery is 90%. Moving outward, the framework layer contains execution sandboxes and deterministic hooks. The outermost layer is observability, crucial for tracking model drift. Agent failures frequently reveal gaps in surrounding tools, rule files, or guardrails, rather than a lack of intelligence in the reasoning engine. This compares the traditional SDLC with its AI-driven equivalent. Historically, moving from requirements to testing took weeks. Now, requirements move straight to implementation, compressing cycles to minutes. This requires distinct automated quality assurance. Output evaluations verify code, while trajectory evaluations verify the agent's logic. This automated verification allows AI to take over deep maintenance tasks. Codebases that were previously considered too fragile to touch can now be systematically modernized, with agents executing framework migrations while respecting the existing architecture. This diagram maps the new framework, the factory model. Here, the developer builds the system that creates code. The human operator sits above the factory floor, defining specifications and guardrails. The AI agents manage the entire assembly line below. Success in this environment relies entirely on providing agents with strict success criteria and automated testing loops, rather than step-by-step coding instructions. Despite these capabilities, teams consistently hit the 80% problem. AI agents rapidly scaffold the bulk of a feature, but the final 20%, the edge cases, integration points, and subtle architectural correctness, demands deep human expertise. This diagram compares two operational modes, the conductor and the orchestrator. The conductor is highly synchronous, providing real-time, keystroke-level steering inside the IDE. Conversely, the orchestrator uses asynchronous delegation, assigning high-level goals to background agents and later reviewing pull requests. Peak developer velocity requires knowing when to use which mode. You do not move faster by blindly accepting everything an AI produces. You move faster by strategically shifting between fine-grained control and high-leverage delegation based on the exact complexity of the task. This graph projects the financial trajectories of the two methodologies. Agentic engineering completely inverts the economics of vibe coding. Building an agentic system requires heavy initial capital expenditure. Engineering teams must invest significant upfront time building robust test suites, configuring the harness architecture, and defining context policies before they deploy a single feature. But that structural investment unlocks a critical financial lever: intelligent model routing. A robust harness can automatically assess incoming tasks. It routes trivial, well-defined bug fixes to cheaper, faster models, while reserving expensive, high-latency frontier models strictly for deep architectural reasoning. The translation of syntax is largely a solved problem. Instead, intent is the new interface for the modern software engineer. They provide the most value by designing and maintaining the resilient, automated factory that ultimately produces the code.